So, what if all those strange things people see in the sky, what if they aren't just breaking the laws of physics, but are actually rewriting them? Today, let's dive into the physics of what should be impossible speed. And look, we're not just talking about some blurry photos here. For decades, really credible people, we're talking trained pilots, radar operators, have been reporting UAPs doing things that just, well, they defy everything we know about physics. Think about it. Instant acceleration, stopping on a dime, making turns that would literally tear any normal aircraft to pieces. And this stuff isn't science fiction, It comes from serious people. Guys like Paul Hill, who is a NASA engineer, he looked at all these sightings as a straight-up aerodynamics problem. And what did he find? He concluded that whatever these things are, they're not using jets, they're not using wings, they're playing with forces in a way that we don't get it. Not yet, anyway. And that right there, that's the real puzzle, isn't it? I mean, forget about the craft for a second. Just imagine you're inside one of these things. The G-forces for making a sudden right-angle turn at thousands of miles per hour, you'd be toast instantly. So the big question is, how could anything or anyone possibly survive that? Okay, so this is what we call the impossible flight problem. It's this huge clash between what credible people are seeing with their own eyes and what our fundamental laws of motion and inertia say should be possible. So how do we solve it? Well, the answer might force us to think completely differently. What if, instead of trying to fight inertia by blasting through space, you move a little bubble of space itself? You're not moving in space, you're moving space with you. And that idea brings us to a concept that sounds like it's straight out of sci-fi, but it's rooted in real theoretical physics. It's often called a warp bubble. The core idea? You literally ride a wave made of space-time. Yeah, back in 1994, a physicist named Miguel Alcubierre came up with this. He created a mathematical model that actually works with Einstein's general relativity. And what it suggests is mind-blowing. You could travel faster than light, not by breaking the cosmic speed limit, but by bending it around you. So how on earth would that even work? Okay, picture a surfer on an ocean wave. The surfer isn't paddling faster than the wave, right? Nope. They're just being carried by it. In this model, the ship is the surfer, and the wave is space-time itself. You scrunch it up in front of you and stretch it out behind you. And this is the genius part. This is how you solve that impossible flight problem. Because inside the bubble, space-time is totally flat, totally normal. The ship, the crew, everything. It's technically not even moving. It's experiencing zero acceleration. You're just in free fall, chilling out while your little piece of the universe gets carted around for you. Okay, but that's the big multi-trillion-dollar question, isn't it? It's one thing to have the math for it. It's another thing entirely to actually build something that can bend the fabric of reality. And as it turns out, there are two totally different ideas about how you might pull that off. All right, let's start with the first one. This is the answer you get from mainstream theoretical physics. We're talking about the path that physicists like Eric Davis and Harold Puthoff have looked into, and it's all grounded in the laws of the universe as we know them. So this approach, it's built right on top of Einstein's equations. The math checks out. But, and it's a huge but, there's a catch. It requires something called exotic matter. That's basically a substance with negative energy density. Or to put it simply, matter that has negative mass. Now, we've seen some teeny tiny hints that this could exist in things like the Casimir effect, but we have never, ever seen or made it in any real quantity. It's purely theoretical at this point. But what if you don't need undiscovered physics? What if there's another way? A path that's all about clever engineering? This is where things get really interesting, because it brings us to a totally different source of information. Not too long ago, an archive popped up. It was full of technical documents from a Soviet-era aerospace engineer named Valerius Chernigayev. And get this, his blueprints describe a way to create a very similar bubble, but not with exotic matter. He proposed using powerful, super precisely shaped electromagnetic fields. We're talking complex layers of solenoid coils, which are basically just powerful electromagnets, all designed to manipulate the vacuum of space itself. No exotic matter needed. So now look what we've got. It's fascinating, right? You have two completely separate paths leading to the exact same idea. On one hand, you have the physicists using general relativity saying you need this exotic matter stuff. And on the other hand, you have the Soviet engineer with detailed blueprints saying, nope, you can do it with electromagnetism.
One is a theoretical puzzle, the other is a practical, though, totally unproven engineering plan.
Okay, so before we all get way too excited, we have to hit the brakes and do a massive reality check. Because the challenges of actually building any kind of warp drive are, well, they're astronomical, literally. Let's go back to Alcubierre's original paper from '94. The amount of energy he calculated you'd need, it was just staggering. We're talking a negative mass equivalent of minus 10 to the power of 64 kilograms. To put that in perspective, that is more negative mass energy than all the positive mass energy that exists in the entire known universe. So, yeah, basically impossible. But, and this is where it gets really exciting, over the years, other physicists have tweaked and refined the model. And every time they do, the energy requirement just plummets. They change the shape of the bubble a bit, and suddenly the requirement dropped from the mass of the universe down to the mass of about 3 suns. Then, down to a few milligrams, and most recently, Harold White got it down to the mass of the Voyager 1 probe, about 700 kilograms. Now that is still a ton of energy, don't get me wrong, but it's not more than the universe impossible anymore. It's in the realm of maybe one day engineering. And it's not just about the energy either. The physics of warp drive opens up a whole can of worms, some really weird paradoxes. For one, any kind of faster-than-light travel could theoretically allow for time travel, which just breaks everything we know about cause and effect. Some theories also suggest the bubble itself would be super unstable, or that it would scoop up particles as it travels and then just blast its destination with a lethal dose of radiation when it arrives. Oh, and maybe the biggest problem of all, the pilot inside the bubble can't actually send a signal to the front of it, which means you can't steer it and you can't stop it. Kind of important. And yet, even with all these massive hurdles, something pretty remarkable is happening here. You've got mainstream physicists using Einstein's equations. You've got a Cold War engineer with these secret blueprints. You've got modern theorists refining the math. And they're all from completely different directions, pointing to the exact same idea. A craft that's shielded from inertia because it's riding inside a bubble of engineered spacetime. There's a great quote from the source material that just nails it. It says, the physicists, like Davis and Puthoff, they describe the physics of that space. They tell you what the bubble needs to be. But the engineer, Chernahiyev, he offers a potential answer for how you might actually build the thing. So where does all this leave us? Is this whole thing just a cool sci-fi dream? Is it a deep theoretical puzzle that physicists are going to chew on for the next 100 years? Or, and this is the big one, is it an engineering challenge that someone, somewhere, might already be solving? When you see all these different paths leading to the same place, it really makes you think. And it feels like this conversation is just getting started.